All right, thanks everyone. We are back. So our next speaker will be Elaine, who's a faculty member at Carnegie Mellon University and the founder of Oblivious Labs.
Okay, I'm very excited to be here. Actually, Quintus emailed me and said, oh, we want you to come to the MEV workshop to give a talk and talk about ORAM. And I said, oh, of course, I'd be happy to talk about ORAM anytime. And then he said, oh, no, but we don't want you to talk about ORAM because we have heard about ORAM. So I'm going to talk about compiler for Oblivious computation today, or in other words, I will tell you, do you actually need an ORAM? Okay, and before I explain whether you need an ORAM or not, let me first explain what is ORAM and what are the applications of ORAM, just very quickly. So I'll just take Flashbot use case as an example, right? So in order to mitigate MEV, a great approach is to encrypt the transactions so that when you build the block, the miners don't see the transactions in the clear. Flashbot has built a BuilderNet, and it has SGX TE support. And then we are going to do the block building inside the trusted enclave called TE. And I want you to think about the transactions as small programs. They are smart contract programs. So as we build the block, we have to speculatively execute these programs. And as the programs execute, they will access data that live on the blockchain. And even if everything is encrypted, like your transactions are encrypted and the blockchain data can be encrypted, the accesses to the blockchain can still leak sensitive information. And in this case, the information that gets leaked includes things like which crypto asset is being traded and who are the sender and recipients. And these are precisely the information we care about hiding. So it is very important for us to try to hide the access patterns to this big data set. Okay, and here's a concrete example to just show exactly what gets leaked. And this is like a Uniswap contract. And if you are going to execute this contract, it's going to access sensitive information like the crypto asset you are going to trade, as well as the account information. So this is the information that will get leaked. And in order to hide access patterns, we can use this powerful tool called ORAM, which stands for Oblivious RAM. And in this talk, I want you to think about ORAM as a generic compiler. And why do I say it's a generic compiler? Because given any insecure program that runs in time t, you can take the ORAM compiler and it will emit an equivalent program that runs in just a little longer in t log n or t log n square time. And this resulting program is oblivious in the sense that the memory access patterns don't leak any information. And the security is provably guaranteed. Okay. So because ORAM is a powerful building block, actually there has been exciting developments in real life. These are some of the use cases of ORAM. Signal has actually deployed ORAM at a large scale, and they use it for private contact discovery, right? So if you actually use Signal and they ask you for your contacts, don't worry, because they're using my algorithm, it's perfectly secure. Ethereum wants to use it to enable private blockchain reads. And actually, yesterday I was on a call with Ethereum Foundation, and we are very excited to collaborate with Ethereum to help them make this happen. And Meta has also implemented ORAM, and I think likely they're using it for private AI, like maybe to analyze data collected from WhatsApp. But I don't know about this detail. The detail, it's an educated guess. I think they're being a little bit secretive about exactly what it's being used for. Okay, so in fact, what's important to observe is that in all of these scenarios, traditional encrypted databases fail. They don't solve the problem, because if you think about it, in all of these, let's say in Ethereum's case, right, the data itself is public. So it's not the data content that we care about protecting, it's actually the accesses to the data. So traditional encrypted databases, they only encrypt the data contents, and they basically don't do anything to address the privacy concern. And so is the case with Signal's use case, because in Signal's case, the data actually Signal can already see the database, and it is the queries that they want to hide. So really what you need is ORAM rather than traditional encrypted databases. So if you want to use ORAM, as I said, ORAM is a very powerful tool. It gives you a generic compiler that can convert any program to an oblivious form. And if you want this generality, it's known in theory that you have to suffer from a log n performance lower bound. And this was proven by Goldrick and Ostrovsky. And we also know that if you make some computational assumptions, like if you assume existence of pseudo-random functions, we can indeed match this lower bound. In practice, we don't use these computationally secure schemes. We use a different class of schemes called, so typically we use either path ORAM or circuit ORAM, and they're based on a new paradigm called binary tree ORAM paradigm. And these schemes, in theory, they get log square performance, but because one of the log has a large base, in practice, they actually just behave like log n algorithms. Okay, so that is ORAM landscape. And having talked about ORAM, I will now try to answer the question, do I need an ORAM? In my earlier talk, I guess maybe in MEV workshop last year, I showed this decision chart. Do you need an ORAM? So pretty much, if you want to use TEE or MPC, you really want to think about this question. Like if your computation task is somewhat interesting in the sense it will make dynamic accesses to memory, then really you want to think about using an ORAM. Otherwise, it may not be secure. But today, I want to give a more nuanced answer to this question. Do I need an ORAM? And the thing is, like, indeed, we want to protect access patterns, but ORAM is not the only way to protect access patterns. And this log n lower bound for ORAM, if you have a concrete computation task, this log n lower bound may not apply. Like you can oftentimes do better. Like for instance, if you want, what you want is just sorting, or you want to run some Dijkstra shortest path algorithm, or you want to run compaction, which is a special case of sorting, or you want to have a priority queue. Like in all of these cases, and there are many, many other examples. In all of these cases, like we often know oblivious algorithms whose performance actually even match the insecure counterpart. Like we don't have to suffer from the log n overhead. So for this reason, like we shouldn't just generically just apply ORAM and, I mean, of course you can do that, but it's just like you'll have to suffer from more performance overhead. Okay, so I will kind of take a algorithms compiler code design perspective to tell you how we can take advantage of this insight. And on the algorithm side, right, so on both sides, we are asking the question, do I actually need ORAM? But more specifically, on the algorithm side, we are asking, given a specific computation task, how can I design an efficient oblivious algorithm, possibly, circumventing the need for using ORAM? And on the compiler side, it's a slightly different variant of the question. I'm given a specific program, and I want to look at this program and compile it to an efficient oblivious implementation. So that's the compiler's goal. Okay, and then when I go over, I will go over some examples, and I will tell you the algorithm's perspective, and I will tell you how the compiler can, be inspired by these algorithmic ideas and automatically emit efficient oblivious implementation. Okay. So idea number one. So this is a very simple idea. It's essentially partitioning, right? So from an algorithm's perspective, we want to look at a program and partition the accesses into ORAM accesses and non-ORAM accesses, because some accesses are actually safe to reveal. They don't disclose sensitive information. And then we can actually automate this analysis using a compiler. The compiler can take a look at your program using a standard technique called information flow analysis. It can figure out whether each access has to be protected or not. Okay, so let's look at a simple example. This is a really simple program. It just linearly scans through an array to find the maximum element. So you don't actually have to read the code in detail, but you can see like the access patterns into the array is just determined regardless of the array contents. And in this case, actually, you don't need to put the array in ORAM. And you can, if the array is actually secret, you can just encrypt it. You don't have to put it in ORAM. But the compiler is still going to, so this is like a side note, like the compiler actually will still inspect the program and rewrite this control branch by padding the else branch. And the reason for doing this is that it wants to guarantee that both branches have the identical traces. So like it should not be the case that an observer can look at the instruction or memory trace and determine which branch is taken. Because if you look at the guard for the branch, this is a secret guard, right? Because, suppose, let's say, the array contents are secret. HI is a private array with secret contents, then this array, this conditional is a secret conditional. So you want to make sure both branches have the same behavior. Okay. So, but nonetheless, we don't need ORAM in this case. And here's a more, of course, the find max is very simple. Here's a more realistic example. Like this is actually a main loop in a Dijkstra implementation. And the details of the algorithm is not important. But if you look at the code, you'll realize that there are three arrays: the distance array, the visited array, and the edge array. And if you look at the code a little more carefully, you'll realize the distance array is always accessed sequentially. And actually, we don't need to place the distance array in ORAM, and we only need to place the visited array and the edge array in ORAM. So with this kind of analysis, and basically, our compiler can automate this analysis. And with this kind of analysis, we can basically avoid the usage of ORAM whenever possible to improve the efficiency of the execution. Okay, so this is the first idea, partitioning. The second idea I want to talk about is we can actually design programming abstractions for obliviousness. So again, from the algorithm's perspective, like one approach is like for every computation task we care about, let's say today I want to implement a heap, tomorrow I want to implement binary search tree, we are going to design a customized algorithm for every task I care about. But this is a slow and maybe somewhat tedious process, right? A better approach is we are going to look at classes of algorithms. So I want to have an understanding for certain classes of computation, I can do better than ORAM. And this is what we are going to try to achieve from the algorithm's perspective. And from the compiler's perspective, we want to be able to design programming abstractions. And if the programmer writes the program in these abstractions, then the compiler can get some insights, get some hints during the compilation process, and avoid the usage of ORAM. Okay, now this may be very abstract, but I can give you an example and you can see like a concrete example. So this is just trying to compute a histogram. It's a very simple program. So this is how you normally write the program, right? You just scan through the array, and then for every element you encounter, you increase its count. And if you do a normal compilation, if you write the program like this, the compiler will see that if your array is a secret array, the array contents are secret, then the access patterns will leak the array contents. So it will decide to put the count array in an ORAM. And this will create some performance overhead. However, imagine the program wrote the program using a map-reduce abstraction. So histogram is something that's very easy to implement with a map-reduce abstraction. Like essentially, for every key you encounter, you map it to R(1), where 1 means I have seen it once. And then the reducer gives an aggregation function that just adds up the count. So if you write it with a map-reduce abstraction, actually the compiler can realize, we don't need an ORAM in this case. We can just compile it to Oblivious sort. And for Oblivious sort, we have like, this is a paper that's going to appear in Usenix this year. And, we have these fast implementations, and the performance will be much better than ORAM. Okay, and here's how the sorting-based solution works. So we have these keys. We want to do histogram. We first obliviously sort it. So the same key will appear adjacent to each other. And then we do a linear scan. And with this linear scan, essentially every element will look at its neighbors. And the last element of the same kind will write down the count during this linear scan. So like, for instance, the count is like apple appears twice, banana twice, and I guess it's wrong. It's like 3. And then finally, you can sort it again. So the actual counts appear in the front and the dummy entries appear at the end. So now you gather the counts for every element. Okay. So actually, this is not a coincidence. We actually have a lot of insights about how to compile parallel algorithms to Oblivious counterparts without going through the ORAM transformation. So in general, the high-level intuition is that if your computation task is parallelism friendly, it can be efficiently expressed as a map-reduce program, or efficiently expressed in the graph lab abstraction, or in the binary fork join abstraction, then actually we can compile it to an Oblivious implementation without going through ORAM. And oftentimes Oblivious sort is enough. Okay, so from a programming language perspective, we are going to allow our programming language to have these programming abstractions. And when the developer uses these programming abstractions, it can help improve the performance of the compiled implementation. Okay, so finally, I want to give you another example of programming abstraction. And for this, I want to illustrate the algorithmic idea first, and then I will tell you how it generalizes to programming abstraction. So it's oblivious data structures. So data structures are used everywhere, right? You know, there are lots of data structures. So let's imagine we have a simple binary search tree, and we want to make an oblivious binary search tree. The most naive idea is that we are just going to use ORAM to compile a plain insecure binary search tree. So let's say we are going to take AVL tree and use ORAM to compile it. With the AVL tree, every access takes log n time. But when you use, let's say, path ORAM to compile it, every memory access incurs log squared overhead, right? So it's multiplicative. Log squared times log n. So essentially, you get log cubed cost per request. And I will tell you a better way to accomplish this so we can save a log factor. And in order to understand the idea, so I will not go into ORAM in detail, but I will quickly talk about how to think about ORAM, because to do this trick, we need to use like a building block that's part of designing the ORAM algorithm itself. So essentially, ORAM is a tree. It's a binary tree. And in ORAM, every element resides on a random path from the root to some random leaf. So let's say, you know, some element you care about resides on this blue path. So I will just abstractly draw the tree as a triangle, and I will draw the path as a line. And then if I want to access some element, I just have to access the path that the element resides on. But besides doing that, I also have to do some maintenance work, which I call relocate on this slide. Like I'm going to get the element I want, but I will also move things around on the path to make sure the buckets don't overflow. So this is like a maintenance operation to make sure that the database, the data structure is well formed. Okay, and then I will, once I access something, I will choose a random new path and assign the element to a new path, but I will not disclose the path at that time. I just write it back to the root. Okay, so essentially every request touches a single path. And then in order to know which path it is, we are going to use a recursion data structure. So how does the recursion work? So imagine I want to read some logical address 01100. You know, I have to first find out which path this element resides on. And in order to do that, I will put, like, imagine I have an array that records where every element is. And I put this index array in a smaller ORAM. And if you take this recursion idea, essentially, you'll have a sequence of trees. And your lookup will start from the smallest tree, which is constant in size, right? Because if it's constant in size, you can just read the whole tree. And then every time I will ask the question, you know, you can imagine every time I'm filling in one more bit in the address, and I will look up the path in the next tree. And then I know where to access in the next tree. And eventually, I will get to the final data tree, and then I will be able to get my elements. So this is the recursion data structure when expanded. And a very simple idea for implementing the binary search tree is that we are going to overlap the recursion structure with the logical tree of the binary search tree. So on the left-hand side is the logical binary search tree, and on the right-hand side is the ORAM tree. Right. Here, I've coalesced all of the trees into a single tree. We can take all the recursion trees, coalesce them into a single tree. And essentially, these pointers there denote the recursion data structure. So like, for instance, once I look up the element 8, I immediately know which paths the two children rely on, reside on. I immediately know where the two children 3 and 10 are. And then because let's say I want to look up 1, I just have to look up 3 next. So what this does is like, essentially you get log squared cost per request, because essentially you are saving the recursion cost. And the naive approach I talked about has like log cubed cost, right? So this is like, by using this clever trick, we can save a log factor. And this idea generalizes to like a lot of other data structures, not just binary search tree. And actually, it generalizes even further, because there's this recent paper by Pan, Heath, and Ren very recently, and they further generalized it into something called Oblivious single access machine. So this paper, although they didn't make a compiler, actually it gives the very promising approach to defining a programming abstraction called smart pointers. And if you write the program using the smart pointer abstraction, we can compile it directly, to this non-recursive ORAM tree without going through the full ORAM transformation, and this can save you a log factor. Okay. So just to quickly summarize what I talked about, do I need an ORAM? I talked about this idea of using a compiler, right? So at the bottom, we have a suite of rich Oblivious algorithm building blocks, not just ORAM, but also Oblivious algorithms for many other primitives. And these primitives will be fed into the compiler is aware of these rich primitives, and then the developer will supply some source code, and the compiler will do optimization and figure out the most efficient Oblivious implementation. And this can both be a TE-based secure computer or an MPC-based secure computer. Both, when you compile to TE or MPC, you have to worry about obliviousness. Okay, and then so there are actually two aspects of the compiler. I only talked about the efficiency perspective today, but there's also another benefit of having such a compiler because it can formally verify the obliviousness of the program at compile time, and this is something that we call memory trace obliviousness. Essentially, you can develop an information flow type system, and like normal information flow type system, make sure that data sent to low outputs do not contain secret data. Like let's say if you are going to send some data to a public network channel, it better be public data and not secret data. And then memory trace oblivious type system extends the standard information flow type system. It also captures memory traces in the type system. So it makes sure that the memory traces do not depend on secret inputs. So even though I don't have time to go into details of this, I want you to keep in mind this is another great benefit of having such a compiler. It can defend against accidental programmer mistakes. Okay, so our just before I conclude, I want to quickly talk about our roadmap. Today we have already shipped a very fast Oblivious key value store implementation. The open source is out there. You can try it out if you want. Our implementation is like an order of magnitude faster than Signals and about 100x faster than Matter's implementation. And we are also working on something called Oblivious STL. This is ongoing. And this is the rich suite of Oblivious building blocks that I've been talking about. And it's kind of like a prerequisite for eventually making a compiler like this. And we already have some primitives available, like sorting, some Oblivious data structures, maybe a few graph algorithms. But it still needs a lot more work. And eventually, at some point, when the Oblivious STL is more ready, we can start working on building an optimizing compiler like the one I talked about. And then Quintus talked about the future roadmap, right? So besides trusted hardware, it would be very nice if some of the cryptographic primitives can also become practical. And then in our research at CMU, we are also looking at the performance of these cryptographic replacements of TE. Like for instance, if we replace TE with two-party computation, you are looking at about 1,000 to 10,000x slowdown, but actually it's still reasonably fast. Like with plain TE for a very large database like Ethereum or Signal scale database, every request takes 20 to 50 microseconds, which is very, very fast. And then with these crypto techniques like 2PC or private information retrieval, we are looking at about, on the order of tens or hundreds of milliseconds. But this is all measured on a single computer. So I think another promising direction besides developing a new secure computer is we can develop hardware acceleration techniques for these cryptographic primitives, right? Because even this is just on a single computer and there's limited parallelism. And a lot of these primitives are very amenable to parallelism, and we can further speed it up to get practical performance. Okay, thank you very much. The talk is based on several of my earlier papers, and I didn't have time to refer to them. But if you are interested, you can go to my webpage and look at these papers in more detail, like for instance, about some of the type system details. Thank you.
Thank you very much for the talk, Elaine. Oh, I have a question. So one thing you didn't touch on too much in the presentation is instructions, but instructions can also reveal information about the data that's being processed. I know that's part of the memory trace obliviousness definition. Could you elaborate a bit more on that? Yeah.
Yeah, so I had like one slide that quickly mentioned it. So this is one example. It's like, if you have a control branch dependent on secret data, you want to make sure that all branches exhibit the same memory trace and instruction trace. And this also secures against timing channel as well, because if both branches have the same instruction trace, and assuming the execution time of the instruction itself is not data dependent, then you make sure both branches take the same time to execute as well. Yes, Phil.
I had a similar original question and also about timing channels. So how do you actually handle that in the ORAM side of things? Does like the compiler like kind of pad things, or does it just assume that you're kind of invariant in like the number of memory accesses and the timing on?
Generally, there are usually 3 ways to defend against timing. One is that you can always develop, like, imagine you are building a secure processor, you can always access memory at fixed intervals. And even if there is no memory access, you will pretend you are making a memory access. So this is like naive approach number 1. Approach number 2 is to use our compiler, which will take a look at your program, and it will essentially pad the program such that you always incur the worst case timing. It will always execute to the worst case for all possible inputs.
So that's even if you're not doing the like full Oblivious, even if you're just doing the ORAM compiler, it does that?
The ORAM compiler does give you full Oblivious.
Okay, cool.
So, but in some cases, this overhead is reasonable, because, like, let's say the worst case and the common case are close. In some cases, if the worst case and the common case are far apart, like let's say you are doing database join, like the worst case can be quadratic and the common case is linear or quasi-linear. And in this case, we also have a line of work called differential obliviousness, and we can obfuscate the timing using differential privacy techniques. So you don't have to always incur the worst case overhead.
Okay, cool. I'll check that out. Thank you.
I think when maybe Afonso also interned at Flashbot, like Afonso is a co-founder of our company. He actually built, but this is still an preliminary thing. Like he built Oblivious EVM instructions, which is kind of taking all the EVM instructions and trying to do this for every instruction, to make sure every instruction will execute in a data independent way, like the timing and the traces of the instruction itself will be data independent. So I'm happy to share the open source with you if you are interested.
So just to clarify, you're saying that the ORAM in your version of a compiler kind of protect this timing attack for the existing like ORAMs like have.
Yeah. I mean, ORAM itself is like it's just going to take every memory access and translate it to some random axes. So
yeah.
ORAM itself doesn't necessarily give you the timing channel protection, but the compiler does.
I see. And does it have a overhead in terms of like obfuscating the timings and for the tracings, or like is it insignificant?
It depends. I think in many cases, like for this EVM instruction at that level, it's like, sometimes you may incur twice the overhead, because you have to pad, like in this example, you have to pad the other branch, right? So maybe the runtime for that particular instruction will slow down by a factor of 2. But I mean, of course, you have like your whole program, not every instruction is like a secret branch. So like overall, how much overhead you incur, it depends on the application itself. And in some cases, as I said, if like this padding is incurring a large overhead, because essentially what this padding will do is like it will pad the execution of your program to always to the worst case. And in cases where this overhead is too large, we can use something called differential obliviousness, which relaxes the privacy notion to like differential privacy. And we actually have some papers on that too. like for instance, we applied it to database join, which is a good example where the worst case can be quadratic. Let's say two-way join. The worst case can be quadratic, but the common case is usually linear or quasi-linear. And in these cases, we don't want to suffer from the worst case.
Yeah.
So we use differential obliviousness.
And that's the efficiency come from for even though you like preventing the timing attack.
Yeah. So the differential obliviousness basically adds noise to the running time. So it obfuscates the running time in a mathematically.
If you do the Gaussian distribution, like a worst case is like a more larger range, but like based on the average case.
Yeah, you can add noise by sampling from a Gaussian distribution. Yeah.